This video gives a high-level overview of some ideas from machine learning. So the basic idea here is we want to design algorithms, machine learning algorithms, that can learn how to perform tasks based on some data that we're going to give them. Okay, so as a kind of motivating example, let's say what I want to do is train an algorithm to decide whether an image that I feed into this algorithm is of a cat or of a dog. Okay, well, this seems like a good fit for the framework we developed earlier, which was binary hypothesis testing. The problem is that we do not have good probability models for cat and dog images, right? So it's not something that you can just write down pen and paper. This is how you generate a cat image. This is how you generate a dog image. So instead, what we do have are data sets consisting of lots of example images. Especially now with the internet, you can get lots of examples and you could use those to design your decision rule. Okay, so supervised learning is the branch of machine learning where you have a data set with labels. Okay, meaning that for every example in my data set, I know both the input, right, and the output, the desired output that I want. And that's output is sometimes called the label. So in that previous example, that would be cat or dog. In unsupervised learning, the data set is unlabeled, meaning that for each example, we only know the input. So I don't know which examples are cat or dog images. I mean, I know as a human, but the algorithm is not given that information. So maybe all it needs to do is just group the cat images together without saying that they're cat, and group the dog images together without saying they're dog. And then I would just look at the batch at the end and put a single cat and single dog label on those folders. And a data set, a little more formally, it's a collection of examples that we're going to write as x vector comma y for I equals 1 to n. And we can think of this vector as the input, and its entries are called features. Okay, so one example could be you're measuring some cells, and these features could be the measurements for the radius and the texture and so on, or it could be the values of the pixels of an image. And this y is the desired output, which is the label. So that could be cat or dog, or in this cell example, it could be benign or malignant if we're looking for tumors. So these features are usually highly correlated. And so we need to do is find a good probability model that captures all of the relationships between the features and the label. And that's basically a high dimensional function. And learning these kinds of functions or probability models requires many, many examples, usually more than we have either available or that we're willing to compute over. So this phenomenon is sometimes called the curse of dimensionality, which is that when you start to get into large dimensions, like for images, then it becomes very difficult to fit a probability model, even for a small image. So let's look at some applications. So as a first application, let's go to the thing that we were just talking about. So it's actually called classification. So what I want to do is place each example that I'm given into a category specified by the label. Okay, so this is very similar to detection. The only difference is that we're operating without a probability model given to us in advance, right? So I have these positive examples and these negative examples, and you could think that in this case, the orange or negative are a cat and the blue or positive are dog. Regression is something we've also thought about from a different perspective. I use the input values to predict the output value and minimize some kind of loss function, which could be mean squared error. So this is very similar to estimation, which we've thought about. But now, again, we don't have a probability model. I'm just kind of trying to fit the best function that I can. So maybe I have this data and I try to fit this curve. And as an example, maybe I'm trying to predict cholesterol levels from other values like height, weight, etc. And finally, let's look at another example, which is clustering. So I'm trying to group examples here into meaningful clusters without access to any labels. Okay, so I have no access to labels and I want to come up with some coherent clusters. So that could be maybe I'm looking through online news articles and without any Human help, I want to cluster them into sports articles, food articles, and etc. So I want to organize them into topics without any input from a person. So as a first step for training a machine learning algorithm, usually what we need to do is come up with a large collection of examples, hopefully with labels. Okay, it's nice to have labels, and that's going to serve as our data set. And it's really important at this stage to decide which features we're going to include in our X vector and which to throw away because they're not going to be useful. We want each example to be in the same format. You can think that that means that they're vectors of the same length. And labeling examples can be super time consuming, right? So that limits the size of these data sets. Well, one great place to start is just looking for data sets that are already available online via some repositories and competitions. And here are just a few examples of what you can find online if you go looking. So there's the SciFar 10 data set. There's Kaggle, which hosts many interesting competitions. They have lots of previous data sets from previous competitions just sitting there. And there are many tutorials to help you get started. There's also the UCI machine learning repository. There's the Google dataset search engine. And there's this website that people maintain called the Awesome Public Datasets, and they host it on GitHub. So SciFar, as you can see here, is just a collection of images with labels. So there's 10 labels starting from airplane, going down to truck, and there are many examples of these images, and you can try to train a classifier to learn these image labels. And you can find pretty much anything that you want on Kaggle these days. So I've been drawing a lot from the UCI machine learning repository and Kaggle throughout the course, and you can go and look there and see what you find. Okay, another technique which is super useful is dimensionality reduction. And this curse of dimensionality that I mentioned means that it gets very challenging to directly estimate probability models and even select good decision rules and so on, fit a regression model as the number of features increases, okay? So one thing we can do is we can just try to go from many features to fewer features. And what we want to do is to do that by transforming the data from its original high dimensional space to a different low dimensional space that preserves all of the important relationships that we need for our algorithm, right? So we can do this mapping just by throwing out coordinates, but ideally we do this in a way that keeps all the important relationships. So just as a visual example here, let's say I'm living in 2D and I want to go down to 1D. So initially I'm living in high dimensional space. I can't really draw high dimensional space, so I'm drawing 2D. I want to find a good low dimensional space. Let's say the good low dimensional space is this line. So what I'm going to do is just project onto the coordinate system established by this line, and I'm going to only keep the value of that point along that line, right? So each point has a nearest projection on that line, right? And then I'm just going to record the values of the points on that line, and now I've gone from 2 dimensions to 1 dimension, and hopefully I've preserved the information that I want. Okay, to kind of wrap up, we're going to look at a case study in a little more detail, which is binary classification. So what we're going to do here is we want to just select a good decision rule given our examples, okay? So here is our space. Let's say it's 2 dimensions. I have a data set with 2 features. That's why it's 2 dimensions. So xi is just xi1 and xi2. And we have plus minus labels. That means that yi is +1 or -1. So here are some examples that I'm given for my training, right? And here is a decision rule. We could come up with lots of decision rules. This is one. So on the top, I decide plus, and on the bottom, I decide minus. So what's a good measure of performance? Well, one way I can measure performance is the error rate, which is the fraction of points that are misclassified by this decision rule. And sometimes this is reported as a percentage. So here I had 12 examples. 2 of them are misclassified. They're on the wrong side of this line. So my error rate is 2/12, which is 16.7%. Okay, so I can write that as a percentage. Sometimes it's easier to parse. Okay, one way we could come up with a decision rule is we could just rely on our knowledge of probability and try to first estimate some conditional probability models. Let's say f of x given y for x given y +1 and f of x given y for y -1. and then apply the ML rule. So this is just detection theory. We can just try to use detection theory if we can come up with good probability models from the data. And how can we do that? Well, what we want to know is there any way we can come up with a reasonable probability model from data? And there are lots of different ways. So a parametric method would assume that the data comes from a certain family of random variables, like Gaussian. And what you would do is you would just estimate the parameters of that family, like the mean and variance. And this converges pretty quickly. And the problem might be it's not the best fit for your data if it's not Gaussian. So here, let's just say I assume the distributions are Gaussian. I'm going to estimate the means and variances from the data. Okay, so here is my data. I'm going to try to fit these Gaussian. So if you look, what's going on here is these tiny dots on the x-axis, the blue dots and the red dots, those are my data points. So if I have just a few data points, I estimate the mean under blue, I estimate the mean under red, I estimate the variance under red and the variance under blue, and I plot the resulting Gaussians. And as I went to the right, I got more data points. So I got more blue points. You can see that x-axis got filled up with blue points on the left and filled up with red points on the right. And I can come up with Gaussians that are a better fit. And now I see I'm going to make the decision that negative is blue and positive values are red, okay? And that's going to be my decision rule. So that's fine. A different approach would be a non-parametric approach. So I'm going to make no assumptions about the distribution family. And this is going to converge more slowly than a parametric method, but it'll get a better fit in general. Okay, so an example of a method like this is kernel density estimation. And what I'm doing is just taking a little kernel, which is like a little function, like a little bump, and just putting it at each data point that I observe. And then I'm taking the average of those functions at those data points to be my estimate. So you can see when I have just a little bit of data like I had above, it's actually the same kind of setting. So if I have just a little bit of data, then I get this kind of wobbly function. Okay, and if I get more data, then I converge to a better fit. And these examples were actually the same thing that I saw before. Okay, so before I was seeing the same data above and below, and you can see that this non-parametric actually got the correct shape, which looks a little bit more peaky than a Gaussian. But the interesting thing is both of them landed on the same decision rule, which is decide blue when it's negative and decide red when it's positive. And this is actually something which has some deeper meaning that you might explore in a later course. Okay, so can we improve upon the error rate of our simple decision rule, the one that we came up with before, this purple line? And yes, we can. So in fact, we can always get the error rate all the way down to 0, either by memorizing the data set or designing a pretty complex decision rule. Okay, so that's fine. We can do that. So let's take a look at something that looks like that. So here's a very complex decision rule. Now I have no errors on my data set. Okay, so my error rate is 0%. That's great. What's the problem with this? Well, I might be overfitting my data. Okay, and then in the real world, because I've overfit my data, my performance might actually be lower. Okay, so here are some new data points from the real world. So I now deploy my algorithm. And if you look at this for a while, you can convince yourself that the simple decision rule is actually doing a better job on these real data points than this complex decision rule that I propose. So how can we avoid overfitting? And the most common approach used today to avoid overfitting is to split the data set, all right? So I have a data set. I'm going to split it into training data and test data. So what is the difference? Training data is going to be used to select the decision rule, all right, and optimize all its parameters. So if I need to plug in means and variances, I'm going to use the training data to figure those out. Okay, so that's my training data. I use that to come up with my rule. Test data is used to estimate the error rate of our decision rule, okay? So now that I have my decision rule, I can just evaluate its performance. And this lets us compare different approaches, but we're not allowed to use it to optimize the parameters. Okay? The training error rate is the error rate calculated only on the training data. Okay, so here I'm going to calculate my training error. So I have made 2 training errors here. So I had these blue points which were misclassified. So it was 2 over 10, 20%. The test error rate is the error rate calculated only on the test data. Okay, so here I had 6 test examples and I misclassified 2 of them. So I'll circle them here. And so my test error rate was 2/6, which is 33.3%. And the idea is that if I'm overfitting, what will happen is my training error will be very low and my test error rate will be very high. What I want is my test error rate to be low because that's my proxy for the real world. It's data that I'm given that I did not use in my training process. So that's what we actually target as a performance metric when we're training these algorithms.